information about the health of the machine. How many hours has the machine been on? What's the motor temperature? What's the resistance level on the motor? This gives them some ability to circulate some very interesting things, both from a proactive maintenance standpoint as well as potential sells. If they are able to go and look at a client site and say, all your machines are maxed out, they're being used all the time, maybe we should bring in another machine or two. Or go into the client and say, hey, we've noticed that out of the 4 machines you've got, this one that's sitting next to the door is getting used all the time. This guy over the end has hardly been used. You might want to rotate those in order to maintain the life and spread that wear and tear. And then it gets even more interesting. They can start to do things like doing analytics on resistance levels. What is the average resistance level that's reached before a machine starts to fail? When should we start to send a tech out proactively and say, hey, your machine has reached a point where it might be having some troubles. We're going to send a tech out and replace the motor on that machine. We think it's going to go bad. We'd rather not have you have any downtime. So this is a big part of what the Internet of Things is about. So in this case, we're talking about exercise equipment. Specifically, in the first year, they're rolling out 20,000 pieces of equipment. The goal for this installation was to at least get them through the first 3 years. And in the first 3 years, the second year, they were looking at rolling out an additional 40,000 units. By the end of the 3 years, they were looking at 100,000 units deployed. So each unit, the exercise equipment's running in firmware. It's an ASIC, a dedicated processor. Well, some of it is. Some of the newer stuff is actually running Windows 7, which is a little bit unfathomable to me for a piece of equipment. I don't know what you do when a machine blue screens while you're running but nevertheless, I guess it provides a rich user experience with a touch screen interface and whatnot. The machines grab 1 snapshot per second. Each snapshot has about 86 bytes of data in it. Rather than sending a message every second, it batches the machines up and sends out 30 snapshots every 30 seconds. So this works out roughly to 112 million snapshots per day. 52 billion snapshots per month, and 634 billion per year, just for the 20,000 machines. As they roll on the other machines, obviously those numbers get bigger. So you can see really quick, Internet of Things applications, numbers get big fast. We're talking about 1,200, 1,300 snapshots per second on average. And given the fact that we don't have users exercising, well, there's some users that exercise in the middle of the night, some that exercise very early in the morning, but there's generally peak hours. People exercise at the same time of day. So you're going to have very high peaks and low valleys in this type of an application. And that's only with the 20,000 machines. The numbers are just bigger. So the 86 bytes of data is a packed binary message. That's how machines work. And in the process of this, in order for us humans to be able to use it, we expanded that data into JSON. And the 860 bytes was a rough swag. It proved to be about pretty accurate. I think the actual numbers are about 1,200. Well, I should say, I think the 860 bytes is pretty accurate. Once the messages were stored in MongoDB over a large period of 23 million messages, the average was about 1,200 bytes per message. So, storing 86 bytes per snapshot for a year works out to about 51 terabytes of data in S3. It's up to 508 terabytes in that expanded form, so in a database type form where you can actually index it and write an application against it. And again, that's only with 20,000 machines. So what does that look like in terms of AWS costs? This implementation was all done in the cloud using AWS. S3, not too bad. $1,500 for a year's worth of data in S3. I think we can live with that. $127,000 per month. That's a little steep. works out to around $6 a machine, which was more than they wanted to spend. So we looked at sampling some data. The other thing we did was, rather than storing that SMS, storing entire years with the data, the reality was they didn't need to store an entire year's worth of data in the live system. When we talk about doing those analytics and going back and doing trends against load resistances, it's ideal to have as much data there as possible. So you don't want to sample that and having a year's worth or 2 years or 3 years. The more data you have, the better your analysis is going to be. So storing it in S3 makes that possible without the heavy cost. S3, okay, yeah. Do ask questions if I'm talking about something. AWS has a couple different storage models. S3 is one of them. How do we explain S3? Probably the best way to look at it is a file-based key value store. So I assign this file a key and say store it, and then I can retrieve that data back later with the same key. So it's running in AWS Cloud. For all intents and purposes, it's infinitely scalable, and the costs are around 3 cents I think it's 3 cents a gigabyte per month. So pretty reasonable cost. And that might be the prices of a year ago microbucks now. So we brought down the cost. EBS is the other type of storage. EBS is the type of storage you attach to a server in the EC2 cloud. And so the storage for the databases we brought down to about $1,000 a month as well by using a combination of 30-second samples and cutting back the window of time storage. So how are we going to capture and store all this data? So this bears a little bit of resemblance to the slide at the beginning. That one's a nice little marketing slide. This is the preliminary slide that I presented the client to talk about what we might be able to do for them. Obviously, they had a couple pieces of the infrastructure in place already. They had a web services API that was written in Node.JS. They had a data portal that was written in PHP. Those pieces existed. There was MySQL in the middle, and they were having problems. So looking at it, we said obviously, MySQL's got some scaling issues. It's not going to be able to scale infinitely the way they want to scale. So what if we look at storing the data in MongoDB, which has a little better profile for scaling? We could also store in HBase. That was another option. But and then Elasticsearch is another option. The reason both Mongo and Elasticsearch are there is that they both have a little bit different query capabilities. Part of the problem we had with this client, and I'll talk a little bit more about this, but they didn't exactly know how they were going to query the data yet, which made my job really hard because they didn't know what kind of reports they wanted. They didn't know. I mean, they had a little bit of their data portal written, but they knew that was only the tip of the iceberg of what they wanted to do. That was the only piece touching on the consumer data, being able to expose to people their workout history. But they knew they wanted to go beyond that. So why Node.js? And like I said, Node.js was pre-existing before I got there. I could have totally rewrite, but I was comfortable with that decision for a few reasons. Node.js is ideal for this because it is a non-blocking, event-driven I/O. It works really well for this large number of machines connecting and sending data back. Node.js is designed to solve the C10K problem. If you're not familiar with that, we're talking about the ability for a single machine, a single web server to be able to handle 10,000 connections. That's kind of just the tip of the iceberg for Node.js. This developer did a test and was able to do 1 million concurrent connections on a single EC2 instance with 50 gigs of RAM. It's pretty impressive, especially if you start to look at that from the Apache world. 1 million connections in Apache is not going to happen. Node.js is very low latency. This is important in this case because when we talk about blue screen machines, it's no joke. If that machine's sitting there waiting for I/O, and the processor's not able to continue doing the other job it has, which is keeping that machine running, that's a problem. So this had to be a very low latency interface so that the machine can get the data off the machine and move on to its next job. They found a excellent binary conversion library that was written in Node.js that made it very easy to parse those messages out. And it's actually, I was surprised at how elegant that library was. So if you're in that situation of, I got to process some binary data, Node's definitely something to look at. They already have the code working, which is a pretty big win. And it's open source. Why Flume? This is probably one of the bigger questions that I've been asked. Flume's a logging platform. We're not logging here. Well, if you look at what logs are events. Just a whole bunch of events. The minute you push a log into Flume, it becomes events. Flume doesn't move logs, similar to some of the other solutions that are out there, which I'm not going to remember off the top of my head. But Flume moves events. So it's proven in processing large volumes of data. Flume came out of the Hadoop project, and it's been proven to be able to stand up to that scale of volume and work in very large installations. As a scalar architecture, flexible pipeline, and I'm going to get more into the details on these. And the biggest win was that there are a lot of different connection options for Flume. Specifically, I was able to find very quickly a Node Flume, there's Node Logger, that's misspelled, package that enabled me to write messages from Node into Flume. There is an existing HDFS sync which works with S3. There is an Elasticsearch sync, so Flume has sources and sinks and then channels, and I'll talk about that in just a second. And then there's a MongoDB sync that was a third-party package. And it's open source. So MongoDB, scalable document store, has a scale-out architecture. By default, a single installation of MongoDB would have a single server master with 2 replicas. And then you can start to shard. And so you take those chunks of 3 and you create 2 of them, or 3 of them, 4 or 6. And it automatically shards your data across those. As a flexible data model, like any document store in NoSQL, we don't have to worry about the schema up front. This was important because they didn't know what they wanted to query. They didn't know what they were going to do with the data. So we needed a way to just say, okay, we're going to capture the data. And since you have engaged just to help you figure out the next part, we're not going to worry too much about that. Mongo's written in C on the back end, so it's very quick. The company had the development team on site had significant interest in MongoDB as well, and had already done some playing with it. It looked like a reasonable solution. Mongo has massive community support, arguably probably the largest, depending on where you put Hadoop and HBase and all that. That might be the only thing that has as big a community support in terms of a NoSQL data store. And it's open source. Why Elasticsearch? Well, first of all, I love Elasticsearch. Very passionate about it. It's a super scalable document store.
How does that work with Mongo's document stores?
So, that's a good question. Why both? Why would I look at doing both? Mongo's built as a primary data store, which works in terms of when I do a query against a data store like that, I say, I want to get this key back. Give me this key back. And it gives me that key back. You can have secondary indexes in Mongo, and you can say, I want to get all the records that match this field value. Elasticsearch is very different. Elasticsearch is built on top of Lucene. It's similar to Solr, if you're familiar with that. It's built around full text search from the ground up. Because of that, it's not designed to do, it can do a very good key retrieval. And it will retrieve a JSON document, just like you told it to store, which is nice. I can also say, give me all the records that have this word in this field. Or I can do stemming, and I can get all the records that look like that in this field. I can do queries very quickly in it that say, give me all of the records where the resistance level was above this, or below that. I can say, show me the distribution of this field. And it will come back and it will tell me, it will give me a record count by value of all of it. So faceting, if you're familiar with faceting. And so that's why. Mongo is not really good at aggregations and some of that stuff. That's really where it starts to get a little weak. If you're
So did you store the full document in Mongo and Elasticsearch?
We did not. That was the plan, and that's what we would have done, but we didn't do that, and I'll get to why in just a second. Not knowing what they wanted to query and how they wanted to query it, that's why I was saying maybe both, because you can't tell me, you're not telling me you want to be able to just retrieve records that look like this. You know, maybe you're wanting to be able to do more of this analytics type stuff. Elasticsearch is a great platform for doing analytics type, real-time analytics. Lightning fast, simple faceting and aggregation. Scales out very well. It's very easy, just add another node. If you don't do anything, they'll actually automatically start talking to each other, which is kind of a bad thing if you set up your first node in the cloud and all of a sudden it connects to someone else's cluster who also didn't configure it properly. Oops. I only did that once. So the first thing you do when you set up Elasticsearch, you want to change your cluster name. And then you can start to play with it. But it's very simple and very dynamic in the way that it scales out and scales in a cluster. Again, it has a very flexible data model, uses JSON, excellent community support, and it's open source. Oh, and it's easy to use. It's got to be the easiest server I've ever set up. Why not Elasticsearch? So here's the answer to your question. It's written in Java. Seriously. Elasticsearch is one of the things that gives me faith in Java. Restores a little bit of my faith. Elasticsearch works so well in spite of the fact it's written in Java. It really came down to the lack of definition from the client as to what their query needs were, what kind of queries they need to run. It's a fixed bid project, so it comes with inherent things like the fact that there's a lack of time. No real good reason. So it would have been a great solution for them, but just was one of those things that we had to cut from the project in terms of cost and time. I love Elasticsearch. So the ultimate solution looked like this. NetPulse is a third party that they were using already, and so they continued to use that. We ended up taking the Node.js, brought the message in, immediately took that message and sent it to Flume in the binary format for compact storage. And then it did the conversion to JSON and sent that to a second Flume pipeline. And then actually they had a need for like I said before, there were two types of data that were being passed. There was the exercise data, and then there was the machine data. So the snapshot data is the machine data, and it's continually generated and was the largest volume. The exercise data still got sent directly to the PHP front end, largely to send it to these guys, because they had an interface written in PHP to do that. Binary messages went through Flume and are stored in S3. The JSON messages get dumped into MongoDB. At any point in time, they could come back in and add Elasticsearch to the puzzle. And a couple different ways they could do that. They could split this here and have a second pipeline coming through Flume that also sent the same data to Elasticsearch. There's also a MongoDB river, although I just recently heard that Elasticsearch rivers are going away, which is a way of ingesting data into Elasticsearch, but I'm sure they're going to replace it with something that we're working to do. So why Amazon S3? Well, obviously we've talked about the obvious, which is that it's a super scalable data store. But there's more to it than that. It's cost effective, had Flume support. This is the real reason. Tight integration with EMR. Anyone familiar with EMR? Elastic MapReduce? Elastic MapReduce. So AWS has a Hadoop as a service option. Allows you to spin up a cluster of machines running Hadoop on demand, do your data analytics, shut the cluster down, be done with it. This is very cool. Managing a Hadoop cluster, many of you have done it, it's a little bit of a chore. For upgrades or pain, it's not really very fun. There's a lot of work in doing it. There's also cost. I mean, especially if we're talking about a cloud, talking about the number of EC2 instances you've got to keep running all the time in order to run your occasional batch job, in the case of this client. Now, if you're running batch jobs all the time, you're running MapReduce jobs all the time, you're doing interactive hide queries, it might be an entirely different story. In this case where they wanted to store the data, they didn't even know what information they wanted to gather out of it, they just needed to store it, and at some point in time, they needed to be able to do some analytics against what was going to be a mountain of data. This is a perfect solution. Gives them the ability to spin a 20-node cluster, very large machines, do the analytics, pull it out of S3, put the results back into S3, job's done. Shut the cluster down and move on. Why EC2? So, if you talked to me a few years ago, I'd have told you I have no idea why. Having used EC2 for the last 2 years now, there's a lot of good reasons. Specifically for this client, the customer needed geodiversity. They didn't need to set up their own data centers across the world. They needed someone who could provide that to them. They weren't a DevOps shop. They were an exercise manufacturer that had a development team inside. Computing power on demand. They needed the ability to dynamically allocate machines in order to meet the needs of their we need to allocate machines in order to meet the needs of the machines. So the machines who were talking to the cloud needed to have somewhere to talk to. If they were getting overcapacity, they needed to be able to dynamically respond to that. And auto-scaling is one way that that can happen. Auto-scaling is very easy to use. I was scared of it for a while, and then I used it, and I was like, wow, that was way too simple. Basically, you go in, you set up a performance metric. When my CPU is over 80%, allocate another machine. My CPU drops below 20%, unallocate a machine. Simple as that. Cloud formations allow you to take that next step. They say, don't deploy a machine, or deploy a formation, which maybe your architecture is not so simple that it's just deploying a simple machine. You've got to have a backend and whatnot that it's got to talk to and whatnot. You can set that all up into cloud formation. You can say, when my CPU gets up to this, deploy a whole cluster.
So is Mongo running up in the cloud then?
Yes. Mongo is running in the cloud. EC2 reduces operational requirements. Don't have to have as much dev staff or ops staff. And it's easy to deploy, undeploy, dev and QA environments as needed. So if you want to have, for a short period of time, a QA instance that mirrors production, has the same size machines, you don't got to go spend the capital investment that you would if you're doing it in your own data center.
One question.
Yeah.
What exactly is
EC2,
EC2?
Elastic Compute, Elastic Cloud Computing. It is a Linux server, or it could be a Windows server. Sorry, it's Amazon's virtual hosting or pseudo dedicated hosting. But an EC2 instance looks just like a Linux box when you log into it.
Okay, cool.
I wanted to note about Amazon, not that I'm an Amazon salesman. If you haven't played with Amazon, they have a 1-year grace period where there's a fair amount of stuff you can get for free for the first year you use them. So it's very easy to go in there and start playing with it, get become familiar with some of their tools, and use the server. So if you have an idea and you want to pay for hosting, that's kind of a great way to get started. And we already talked about EMR, so I'm going to kind of breeze through this. Spot instances. Amazon has essentially 3 different pricing models. They have the on-demand, which is the basic retail, I need a server, give me a server. If you know you're going to need that server for a long period of time, they have reserve pricing. So you can say, I'm going to need a server for a year. I'm going to need it for 3 years. Reserve pricing brings the price way down. Then they have another option, which is spot instances. Spot instances are a little tricky. Spot instances is a market that allows you to bid on unused EC2 capacity. So all those servers that are waiting to be bought, you can say, I'll give you 30 cents an hour. I'll give you 3 cents an hour. Some of my cases, I give 2 cents an hour in order to borrow hardware for a period of time. Now, the downside is, if someone else wants to pay 50 cents and I'm paying 2 cents, they'll shut my servers down. The S3 integration is, again, was an important reason why EMR. Okay, let's talk about Flume. A lot of this is about Flume because I think Flume was kind of what made this all work. It was kind of the glue that pulled it all together. Flume is nice because it's modular. We've got a source. There's source modules. There's many different kinds of sources. There's a channel. There's several different kinds of channels, and then a sink. Using that modular infrastructure, you can write your own sources. You can write your own sinks. I was shocked at how simple the code was for the third-party MongoDB sync. It was just, I mean, it was a single file, a single Java file, and the code was easy to follow. It's not always the case with APIs. So, because it's so modular, because they've done a good job with those APIs, it's part of what I like about Flume. It's also scalable because it's very easy to take a sink and have a sink right to another source. And so I can fan out, and I can have all my machines talking to these guys, get the load off the machines, and then do whatever processing needs to happen, and fan back in, store it in the database. I could have one fan-in point for Mongo, I could have another one for Elasticsearch, or whatever my solutions are there. And so you can see how dynamic the architecture is. It becomes even more dynamic. A source can write to multiple channels. Each channel can write to a different sink. And then that sink can write to another source, or it can go directly to a data store. Or it can go to JMS, and who knows what you do with it after that. Configuration, pretty straightforward. So the top level of the configuration, we define our sources, our channels, and our sinks. So in this case, I'm allocating 2 of each because I've got 2 different pipelines that I'm building here. There are about 5 different types of channel that are built in. The first is memory, which is what I used in this case. I used a memory pipeline because not every message was that important. If I dropped a message, it wasn't a big deal. But I didn't drop any messages, so it worked out really well. The only reason you would drop a message is if you were overflowing your buffers, if you were exceeding the capacity. They have a file-based channel, which is a durable store. It guarantees that any messages that come in get written out eventually. They have a hybrid memory durable, so basically a memory store that will spill to disk if it needs to. There's a JDC backed one. It seems like there was another one, but I can't remember what it was. But we define the capacity of the channel, 1,000 messages. We tell it that we don't want any transactions going through there that are greater than 800 messages. And I don't recall what the keyblad does. That was just a default value. So defining a source, also very simple. So we're setting up a Thrift source. We tell it we want a Thrift source. We tell it we're going to connect that Thrift source to the bin channel. We give it an IP address, a port, and we tell it how many threads we want that source to run. Along with the source, there's a concept of interceptors. Interceptors are kind of cool. They allow you to modify the data in transit. So this interceptor applied a timestamp. Actually, I defined 2 of them there. It's a timestamp and a host. So one of them applied a timestamp to the message so that I know what point in time that message was received on the bus. The other is the host value, so I know which front-end node received the message. Along with that, with the interceptors, it's possible to use morph lines. So if you're familiar with morph lines, it's a very capable message modification library that's written for Hadoop. Mongo sync, equally as simple. Just basically, I'm going to use the Mongo sync. Here's the host, here's the port. Single basically says I'm writing to a single collection in Mongo. So it's possible to have the message itself tell you what collection it's going to get stored in. So that's another option. In this case, we're writing everything in the same collection. We're going to sync it in batches of 100. It's kind of the things that are nice about Flume is that it takes care of things like batch writing and into your data store. You don't have to write the code to make that happen. S3 sync. This one's a little more complicated. So break it down a little bit. Oh, that's too dark. Okay, no, it's not good. we define it as HDFS type. The HDFS libraries know about S3 and are able to write S3 just like with an HDFS location. We connect it to the bin channel. We tell it that we want our file prefixes in S3 or your key prefixes to be workout snapshots. We tell it that we want it to roll the file after 600 seconds. So if the file hasn't rolled, then go ahead and create a new file. And if everything is idle for 900 seconds, then, so the first one's kind of a minimum, the second one's a maximum, if I recall correctly.
What do you mean?
So send a batch of data up to S3. So S3 doesn't give you the ability to append as you go. You send a whole chunk of data. You kind of can keep the stream open, but it's get really nasty. So what happens is Flume takes this data and stores it locally until it reaches the level at which point it needs to roll a file. And when it rolls a file, then it takes that file and uploads it to S3. So persist would be the equivalent word. When you're doing MapReduce processing, you want files to be large. I mean, large-ish. 256 megabytes is a pretty good size. The reason for that is there's a lot of overhead in, okay, first of all, in MapReduce, each file gets associated with an instance of the JVM. So if you have lots of files, you spin up many, many JVMs. I can kill that. The first project I did that and it didn't work too well. My batch jobs were taking forever. And so I found a different way to deal with that. If you have a big file, MapReduce is all about being able to stream large amounts of data into that JVM and then process it. If the files are too big, it can actually split them up, but it can't aggregate them dynamically. So we kind of want to target 256 megs as a size. So the parameters we put before might thwart this if you're not getting enough data in, but this would be the stop to say, hey, at 256 megs, that's where we're targeting. Let's go for that. This might also thwart it as well. We told it we wanted to not to have any messages, any files that had more than 100,000 messages in them. Part of that's because you want to make sure the data gets up to the cloud before too long. You want to get it persisted. You don't want it sitting on your server that might go down. A couple different options in terms of how you store that data in S3. They largely depend on how you're going to do the processing in Hadoop. So Hadoop has a sequence file input, which is a specific format that's a little bit more optimized for MapReduce processing, or a data stream, which is very just a straight up text. And in this case, we used the data stream initially. I think we eventually might have moved to a sequence file, but there's also the option for a compressed stream. I know we either use the compressed stream or the sequence file. The compressed stream is basically just a data stream that's been compressed with gzip compression, or about 4 different flavors of compression that Hadoop likes. So one of those, gzip is pretty good, but there's a couple others that are a little more CPU friendly. Right format text, again, that goes back to how you're going to be processing the data in Hadoop. And then what's the path look like? So let's break this down a little bit. So it's an S3 path. This is how it knows that it's actually an S3 scene. Your AWS API key, your API secret, and then within AWS, the first part of this path here is called the bucket, and that's basically tells where the bucket's created is where your data is going to get stored. So buckets are assigned to a specific region. The namespace is global, and so your bucket can only, a bucket need only use node space. And since I did this, I've moved more towards using my domain name in my bucket names because of the globalness. It's not global within your account, it's global. Bucket names are global. And then we got the key name. Flume automatically will fill in these, expand these to the current timestamp. So it makes it really easy to have timestamped keys, or they look like directories in your S3. In this case, we wanted to have 15-minute bucket intervals, and so we told it we wanted to round the time. And we want to round it to 15-minute intervals, and the interval is 1 minute. So versions are important. I told you I found a Node library that would allow me to talk to Flume. So I downloaded it, installed it, plugged it in, and could talk to Flume. And I was just like, oh, what's going on? So turns out that Node logger was built for Flume version 1, not Flume NG, which is the current version. I did a lot of searching. Didn't find a solution, actually.
That should have been your business opportunity.
Yeah, well, it turned out, in the end, well, who thought? What happened is that Flume NG changed the Thrift definition. If you're not familiar with Thrift, if you're familiar with Corva or, I don't know, there's a number of others out there. It uses an IDL, a definition language to define the interface, and then you compile stubs for the language you're writing for. Flume NG had changed their definition of that interface, and so that's why the old library couldn't work. Not only did it change that, but Flume has a few different protocols, and they had, or not Flume, Thrift has a few different protocols, and they had moved to using the compact protocol. It got more complicated, but thank heavens for open source. I found that the C++ libraries existed, and they had the T-compact protocol. C++ Thrift libraries were supported. It's pretty easy to plug in C++ into Thrift, or into Node. So it looked like, well, maybe I can write a C++ library using the T-compact protocol, and then plug that in as a library into Node. So I went down that route a little bit. My C++ code wasn't strong enough. And the Thrift libraries weren't documented well enough. I could not, for the life of me, figure out how in the world to write the asynchronous code. I'm not even sure it was possible. I don't know if the C++ library supported the asynchronous version of Thrift in the T-compact protocol. So kind of ran up against a brick wall because Node.js needs asynchronous I/O. Randy Abernathy steps up from the Thrift team, sending an email to Liz and saying, hey, I'm not sure, I'm just confused or what. He says, you're not confused at all. T-compact protocol doesn't exist in the Node library, but I think I can have it done this weekend. Open source. The guy's, I don't know, the guy from Adam, and he did it. He had it up and running, implemented it. This was last March. It was actually 2511 went out in November as part of the stable release. And so now, at this point, while it could have been a business opportunity, once that happened, this became very simple. Yeah, closed source is a bummer. I wish I could show you samples of the code because it's very simple. And again, it's very simple, so it shouldn't be too hard to reproduce. Unfortunately, this was a work for hire, and so I wasn't able to contribute this code back. I wish I was. But pretty simple. Download, install Thrift, run this command here, and that will generate your Node stubs in order to communicate with Flume. And then I didn't like the API that the client and server generated. And you don't need the server, you just need the client. And so I wrapped the stubs up into a little bit cleaner interface for Node, something that felt a little more Node-like to me. Not that I know much about Node, but from what I was seeing, what I liked. And then I was sending messages to them, so that went pretty fast. Okay, I'm going to blaze through this. This is just basically we did some validation on the architecture. We had two front-end nodes, they were M3 mediums, and then the MongoDB replica set was running on M3X larges. We sent 40,000 requests per minute to start. Actually, we started at 20,000. Test ran over a period of 3 hours. You can see that we stepped it up, and we can see on that top line a little bit of not quite consistent, and you'll see why that happened. So here's the CPU during that same period of time. We pegged the CPUs. So at the point where we pegged the CPUs, things got really consistent. But this was running with 2 nodes. Their plan for deployment was a minimum of 6 nodes. They wanted to deploy 2 nodes in Europe, 2 nodes in Asia Pacific, and 2 nodes in Pacific, in California. Latency, when the machine's not loaded, latency was stellar. I mean, even at the top, we're talking about 40 milliseconds there. So latency was really good on the platform. This is Mongo. At first, when I saw this, 2.5% is my maximum CPU utilization. I didn't think I was getting my data to Mongo. I didn't think it was mapping up there. Went to check the network graph, and sure enough, got a lot of network traffic going to Mongo. Went and checked the record counts and found that I had the records there.
So, did you guys try DynamoDB at all, or was it not a good fit?
I can talk with you more. Okay. I had previously tried DynamoDB. It would have been a challenge for them to integrate with a PHP application. It was a much easier fit to switch in. They were using a PHP framework called, I think it's Symfony as the framework, and then, I'm not a PHP guy, so, but there's the ORM they were using had a pretty straightforward plugin to Mongo, which facilitated a pretty quick turnover. We did some testing on a failure, only on the front end, which I'm going to show here. But we basically dropped one of the front ends out of the tube and brought it back. You can see that we took a little bit of hit in throughput, and latency went up quite a bit during that period, but we were able to restore it. And we found that the node servers, each individual instance of the node server was capable of handling 10 to 20,000 conservatively requests per minute. The MongoDB instance we had could have served 20 or 30 node front ends, and the latency was excellent across the board, and the architecture could handle failures. We ingested 23 million snapshots in a period of 3 hours, and Internet of Things is here. Things generate a lot of data, and I love the opportunity I had to work at that one.
Generating more data than us.
We're connecting more things. Oh yes, things are very capable of generating more data than us because they send out 1 second snapshot as fast as we can tweet. We can't quite keep up with that. If I were to redo this at this point, I might look at Couchbase instead of MongoDB. I like the way that Couchbase scales a little bit better. If you have more questions about that, check out my slides. Avalon did a benchmark against the two, comparing the two of them, and Couchbase was a very clear. So that's it. I don't probably not much time, but any questions I'm talking